Okay, so let's go ahead and let's start on 10.1. The first thing I'm going to talk about is the number E, and the number E is a big deal in economics. I mean, formulas that you use, like the loan formula, annuity formula, they all have E in it, okay? So anybody that's going to study business or economics needs to know what E is, okay? E is a number, the decimals go on forever, okay? I just took this screenshot of this on the internet, so they go on forever. For your purposes, it's usually good enough if you know it's about 2.7, roughly, okay? Kind of like pi, you usually use 3.14, E about 2.7, roughly, okay? So what I'm going to do is I'm going to show you how this relates to calculus. First of all, we're going to put something in our calculator, so I want you to do this with me, and then I can probably a little bit later in the section tell about where this came from. It actually came from the mathematician Euler, investigating compound interest several hundred years ago, and he discovered this famous number E. Okay, it just kind of popped out of a business problem. Okay, so this is what I want you to put in your calculator. We're going to put in this function right here. Okay, so we're going to go to y1 and just put it in exactly the way I've got here. You'll go parentheses 1 plus 1 over x, then close the parenthesis, and then raise that to the x power. Okay, that's a function, and that actually has something to do with the compound interest formula, which we're going to talk about in this section. Okay, so now what I want you to do is get a window. I'm going to have you do just kind of a basic window. To start with, let's go like 0 to 20 by a scale of 5, and then I want you to go 0 to 3 by a scale of 1. Okay, and I'll slide this over here and put that window in. Now type graph. If you're with me, type graph and see if you don't see a curve kind of going like this, kind of raising up and kind of going like that. Okay, is that what you're seeing? Okay, so what happens on this, now what do we call it if the graph levels off? What do we call that little dashed line? You remember that? Horizontal asymptote, right? So we have a horizontal asymptote. So let me show you what happens on this. You can just watch this if you want to, but if I go second graph to open up my table, what you're going to notice on these numbers is as x gets bigger, what's happening to y? It's getting bigger. It's getting 2.6. What do you think it's going to go to as we continue to get bigger and bigger and bigger? Probably goes to E. That's probably the plan, okay? So yeah, if you went further and further on that, you would get closer and closer to E like this, okay? So this is basically what I want you all to do on your graph is just kind of this. I just want you to kind of sketch. All you got to do is really put like a 20, maybe a 10, that's good enough, and then go 1, 2, 3, like that. And then what I want you to do is probably put like 2.7 there, and then put a horizontal asymptote there. And then we're just going to get a couple of points, and it's good enough. Okay, so what I'm going to do is I'm just going to trace out a couple of points. Okay, well, the thing is, if I trace at 0, I'm going to show you what happens. I get y equals blank. What do you think that means? Y doesn't have a value. Do you have any idea why that came out on this problem? Okay, there's kind of an asymptote, but look at this. What's wrong with x being 0 in that formula? Can't divide by 0, right? Okay, so you got an error there, okay? Let's go out to let's get 2 more points. Let's trace at, say, 1, okay, something pretty close to 0. Well, that's 2, okay? So let's just go over 1, up 2, and then maybe label that as the point 1, 2. I'm just going to get one more point. Let's go all the way out to 20. So if I trace at 20, that's like 2.6 or something like that. So on this, just put another point there, and let's label that as 20, comma 2.65, like that. Okay, so here's what your graph does. I want you to just kind of sketch this out. It kind of goes like that. It never hits the y-axis because it's undefined, so it just does that. So the idea of what's going to happen on this is as x gets bigger, you're going to get closer to E. That's the idea. That's actually what the definition of E is, and it comes from the compound interest formula. Okay, so here's the idea. When you do the limit as x goes to infinity, the graph is leveling off at E. Okay, and E is approximately 2.7. Okay, like that. So it'll never hit 2.7, the exact value of E, but it gets bigger and bigger forever. Tell me if that makes any sense to you, what we did graphically. Okay, at least I want to give you an idea where E comes from, all right? So I took this thing off of the internet, and this just shows this graph like this. So when you get out to N being 100,000, so if I make it all the way out to 100,000 on my graph, well, I'm 2.71827. So it's closer and closer and closer to those values. So that's the idea, is N gets bigger, we get further out into the decimals of E. That's the idea. Does that make any sense to you? Okay, I think we know this to the trillions of digits. That's the same thing on pi. We know it to the trillions of digits. All right, and we're investigating that mathematically for certain reasons. There's certain things we're interested in. And the digits are random. I mean, they just come out random. You couldn't predict what comes next in a digit on E or pi either way. All right, so that's kind of the graph I wanted to start you with. So this is the definition. You have to know calculus to understand really what E is, and that's why a lot of times students kind of get in this class with kind of a shaky background on what E is, but you've learned probably maybe how to use that in certain formulas. Okay? All right, let's go to the next page, and this stuff probably be familiar to a lot of you. I think this is just kind of your basic simple and compound interest formulas, so we're going to go over that today. So these formulas here, the simple interest formula is I equals PRT. P is the principal, that's what you start with. T is the time. One thing that I would recommend you write on your notes is that's going to be in years. Typically, you want to convert it to years if it isn't. And then this interest rate is usually a yearly interest rate as well. Okay, simple interest isn't used very often because if like you bought a house and the bank charged you simple interest, you probably would never pay off your house. The interest would be ridiculous. Okay, usually something like a pawn shop or a payday loan place, something like that that charges astronomical interest uses this formula. Okay, then the next thing is this formula here is A is the amount in your account after interest. So if you just take the principal and add the interest, then you get the amount that would be in your account. You take the principal, add on the interest. So if it's like a savings account, that's how that will work. And then what I did is, since I is PRT, I plug it in there, and I factor out the P. So if I factor out a P, I get this expression right here. So ultimately, you want to know that formula, probably that one, and then maybe that one. You can get by without that P times 1 plus RT. If you remember A is P plus I, then that's good enough most of the time. Okay? All right, and then here's the compound interest formula, which is totally different. P is the principal. R is going to be the annual interest rate. M is the number of times that you do interest in a year. So if you do compound interest, you might do it every month, you might do it every day, you might do it once a year, twice a year, something like that. That's what that means, and then T is time. Okay? So what we're going to do mostly in this section is just kind of work through these formulas, and these are usually pretty easy to do. The first thing is you got to know what formula to use. Okay, so this one right here says how much money will be in an account after 1 year if $1 is deposited at 100% compounded annually. And this, by the way, is where the number E comes from. Okay, so what I would suggest you always do first on this, since it's compounded, you're going to use the compound interest formula. So I would go ahead and write down the compound interest formula. Okay, like that. And then we'll identify everything we know, and then we'll use a calculator to get this put together. Okay? All right, so let's see if we can do this now. All right, so let's identify what we have. P is the principal. What do you think the principal is in this problem? $1. Okay, so you're putting $1 in your savings account. Okay, good. Okay, let's see. What else you got to know? You got to know the rate. What's the interest rate? 100%, but when you do 100%, you want to move the decimal back, so that would actually be 1.00. Okay, so 100% is just 1. All right. Okay, then the other thing it says is, of course, the time. It says the time is 1 year, so we know that. Okay, and then M is the number of times you compound. Okay, annually means that you do interest one time. At the end of the year, you do interest one time. Okay, so that's what you got, right? This is actually how Euler came up with E. He just discovered the letter E, or the mathematical constant E, out of doing this. Let me show you what kind of he did here. Okay, so what we'd have here is the principal would be 1. Then we'd say 1 plus the rate. Their interest rate's 1. M is 1. And then M is 1 and T is 1. So it's just that basically. Okay, so if you work this out, you would have 1 times 1 plus 1 to the first power. You don't need a calculator on this. So that would be 1 times 2 to the first. So that's $2. Okay, that's it. Now what happens is, what's significant about that is if you did the compounding more often, like if we decided to compound every month, you know what would happen to that 2? It'd get bigger. It'd start getting to be 2 point something. You know what would happen if we did interest every second? That would get close to what number? What do you think? What number did we just learn about that had to do with 2? E, okay? So the idea is that M gets bigger and bigger and bigger, then it gets closer to E. So if you put $1 in the bank at 100% interest and compounded it like in every second, you'd be close to $2.70. Okay, that's how he discovered this number. Yeah.
So the only time when you simplify or divide the time is when it's in months?
Yeah.
It's 12.
Yeah, if it was compounded monthly, then M would be 12. Okay, if it was compounded semi-annually, that would be 2. That's every 6 months. So that goes like that. All right, so that's the Euler thing. That's how he came up with the idea of E. Okay. All right, so let's do this. This says how much money will be in an account after 10 years. 1,000 is deposited at 6% compounded monthly. So again, what I would do on this is I would write down the compound interest formula. And we're just going to look at some different illustrations of this then. Then I would write down what you're given in this problem. Okay, let's start with the principal. What's the principal? $1,000. Okay, this time we're putting $1,000 in. Okay, the time is 10 years. Well, that's always going to be in years. Okay, let's see. The interest rate is 6%. When you change that to a decimal, what do you get? 0.06. Be careful, you go over 2, not 0.6. 0.6 is more than 50%. Okay, so that would be 0.06 when you do that. Okay, what is the M? Because M is compounding monthly. So how many times do you do that in a year? You do 12. Okay, there's 12 months in a year, so it goes like that. Okay, so now we just put this in, and you're going to do this on a calculator. So when we plug everything in, the principal is 1,000. We would have 1 plus the interest rate's 0.06. We'd divide by 12. The exponent M is 12, and then the years is 10. So that's how that gets set up. And you can pretty well just do these problems in one step on your calculator. You don't need to do multiple steps. These are real good calculators you got, so they should serve you well. Okay, so I'll just go 1,000 parentheses, 1 plus 0.06, then divide by 12, close the parentheses, and even the exponent, you can do the exponent in your head, or you can even go just 12 times 10. I'm just going to do 120 because I can do that in my head. Then I press enter. The answer should be something more than 1,000, right? Because you're gaining interest on that. So it would end up being, A would be just about, in dollars, $1,819 and about 40 cents. You're always going to round things off to 2 decimals when you're talking about money, okay? So how much interest did you make off of this account? About $819, right? Okay, so that's the interest that you earned on that. So the other thing you can kind of do is just the interest earned. All you got to do on that is just take the amount that you ended up with after the interest, subtract off your principal. So you made about $819.40. Okay, that's a pretty long-term loan. Or like you can think of this as a savings account, and 6% interest is pretty generous for something like a savings account. Okay, so that's the idea. And the further out you go in time, 10 years, the more money you make. And the more often you do the compounding, the more money you make. That's the idea. Okay, is this familiar to most of you? always seems like when I teach this class, students have at least had some experience with these formulas, which is good, okay, because we're going to kind of, next week, we'll start getting more into the calculus of how this kind of stuff works. Okay, so this, what I wanted to show you here was, this is just basically showing you a kind of a chart here. So if you're doing annual interest, M is 1, semi-annual 2, quarterly 4, and so forth. If you do daily, a lot of times you'll see 365 or sometimes 360. Sometimes it's a common practice to use 360, okay? Hourly would just be taking that 365 times 24 to get that, okay? And this is basically the, if you had a problem, notice on here what's happening is the more often you compound, what happens to the amount of money? It grows, right? That's what you would expect to happen, okay? So it just grows, but it doesn't go to infinity, by the way. Students sometimes think, well, okay, it's just going to go to infinity. No savings account goes to infinity. What this thing is going to do is once you get into hourly and secondly, it isn't ever going to reach much more than $112.75. It approaches a number like an asymptote does. Does that make sense? Okay, savings accounts don't give you infinite money. Okay, it's not designed that way. All right, so that's the idea. Okay, so I'm going to give you 2 problems to try here, and just use your calculator. I'm just going to write down the compound interest formula for you so you can refer to it if you don't know it. Now, I think that's the way the book does that, is they use M and T. Yeah, so that's that. And just go ahead and see if you can get these put together. Daily, go ahead on this one and use 365. When we start getting into doing some work on my math lab, they may tell you to do 360. I don't remember. Okay, I'll just walk around and just kind of see if you're putting things, if you're setting things up okay. You can write it down or you can do it with your calculator.
Yeah.
Saves you to do that, okay, if you want to. That's what I got. Yeah, I think you got it. Yeah, that's what it should be. Be careful on those phone calculators too. Sometimes the parenthesis keys don't work great. That's right.
So do you have to like multiply this like before so I'm just trying to plug in like this. Like,
Yeah, well, what you'd have to do on this older calculator is you'd have to have caret, and then in parentheses, you could have 365 times.
65 times 5?
Yes.
Yeah, because I did that and I'll show you. So
If you don't put that exponent in parentheses on those older calculators, then you do it right.
yeah, it's pretty sensitive.
Yeah, so you gotta be careful.
So like for example, I would do the caret and then I would do like
There you go, now it works. Just have it one whole
Oh, one
parenthesis.
whole parenthesis.
5 times 365. Because then see what it's going to do there is it's going to work that out to get that 18, whatever you've got.
Yeah. Oh, okay, sweet.
Yeah, that's how you got to do the older calculators. It's like that. So what are you getting for the first one? 6 something? 6,500 and something?
Yeah, 6,500.
$6,582.52.
Yeah.
Right? Okay, that's what I thought. Okay. Then the next one is you're only putting $25 in the bank, but it's for 50 years. Yeah, I wish I would have remembered to do that like 50 years ago. When I was a little toddler. I didn't have $25 then. So I think that goes up into the 30,000s or something, if I remember right. Okay, so let's see. Yeah, 6,582.52. It looked like I didn't see anybody having any trouble with that. The next one, let's see, principal's 25, interest rate's 15, so that would be 0.15. Semi-annually is 2 times, so you would do that. Okay, now here's what I got. You can tell me if you got this. I got $34,576.93. Okay, does that look good? Okay. All right, is that making sense to everybody okay? Probably a lot of you have done this before in some other class. I know if you do finite math, I think you do some of the business stuff at a little even a little higher level than this then. Any questions about anything? Okay. Okay, so let's see. Let me go ahead and do talk about continuous compound interest on the next page and just work with that a little bit. Okay, so continuous compound interest just means that you would be doing interest at each instant in time. So this is actually kind of like the optimum thing that would happen. So if you did interest at every moment in time, then that would give you the maximum amount that you could get, kind of like what that asymptote is approaching then. So the formula is A equals P-E R to the T. Or no, I'm saying that wrong. E to the RT, like that. I mean, everything means P is the principal again, E is the number E, and then R is the interest rate, and then T is the time. Okay, so this, we're not going to go really for where this formula comes from too much. I always think of this because every morning when I take a shower, I wash my hair with Pert shampoo. I did this morning to get that lovely sheen. So I think of it as the Pert shampoo formula. Okay. So it helps me remember how that goes, okay? All right, so what we're going to do on this is we're going to just kind of work with the formula a little bit. This one says find the amount if the interest is compounded monthly, and then we're going to go hourly, then we're going to go continuously, okay? So to begin with, the first two problems, we're just going to use the compound interest formula. Okay, and we're going to do that, and then when we get down to part C, we're going to use the Pert shampoo formula. Okay, so it goes like that, all right? And we're going to see kind of what happens on this. So to start the first one, you guys did a good job a minute ago in doing these. You'd have a principal of 1,000, 1 plus the interest rate. Did I give you an interest rate on this? Yeah, okay, I got to give you one. I have to. So let's see. Let's go through and let's make the interest rate like, say, 5%. Okay, just add that into the problem. So then R would be 0.05. Compounding monthly would be 12. then we would have to the 12 times, and then it's 5 years. Okay, so 12 times 5 like that. Okay, and we'll just kind of work at each one of these things out as we go. So let's see. Again, you can do this in one step on your calculator. So 1,000 times point. No, teacher. Do 1 plus 0.05 and then divide by 12. Okay, then raise to the 12 times 5, 60. Okay, you can even put 12 times 5 in your calculator like that. Okay, so that'll give you this amount. So that is about $1,283 and about 36 cents. Okay, so that's how that one goes. Okay, now we're going to do this hourly. So when we do this hourly, okay, it's the same compound interest formula again. Okay, we're still starting with the $1,000, so we'll have $1,000. Then it's still the interest rate of 5%, so that would be 0.05. Now it's hourly, hourly. So what you have to do on this is like this, okay? You can figure out that number pretty easily in your head. Well, let's see, there's 365 days in a year, and there is 24 hours in a day. So we're going to use that number right there, 8,760. Now, if you go back to the previous page, I'll come right back. Hourly is 8,760, but that's where that comes from, okay? So you can always figure that out. So we would have over 8760, and then the exponent m is 8760, and then the time again on this is 5 years. Okay? The answer to this problem going to be bigger than the previous problem or smaller? Bigger, a little bigger. Okay, that's what we'd expect. Okay, so we'll go 1,000, and then we'll go times 1 plus 0.05 divided by 8760. Okay, and then raised to the, like this. Now, those of you who got like an 84, you can just do 8760 times 5. If you have an older one like an 83, you have to do like, you have to kind of put it in like caret parentheses 8760 times 5. I was showing somebody that over there, I think. Yeah, I was showing you that. Okay, so anyway, let's see what that gives. Okay, so that would be a little bit more. So that is giving me $1,284.02. Okay, so we gained a little bit of money just off of doing the interest more often. Okay, what's that? Yeah, just a little bit more, but not significantly more. Because what happens, it starts leveling off. Now, when you do the continuous compound interest formula, it's going to be even more. So when you do this, you're going to go plug in the principal, which is 1,000. You have E. I'll show you where E is on your calculator. The interest rate, again, is 0.05. So we'll put a 0.05 there. And then the time is 5 years. Okay, so you go like this. Now let me show you on your calculator if you're not familiar with this. You'll see like in the last column, you'll see pi, then you'll see E. Okay, so like for instance, if you want to get E to come out on your calculator, you go second and then the division symbol, that's E. Okay, and that's what that value is. Don't use 2.7. Use the E key so that you get greater accuracy. Don't round it off. So what I'll do on this problem is just do 1,000. Then you can go second, division symbol, okay, then raise to, and then you can just do 0.05 times 5. So the answer to this problem should be a little bit more than 1284.02. Probably not a whole lot, just, well, okay, maybe we gained a penny, okay. So it looks like on this it's going to be $1,284.03. Remember I said, these things don't go to infinity. They just start leveling off and approaching a number. But that's the best you can get. That's the best you can do on that is to do continuous compound interest. Okay? Okay, does that make sense? Okay to everybody? Okay. Okay, let's do this problem, then we'll take a break. So go ahead and do the next one. This one's continuous compound interest. So remember, the problem tells you what formula to use. So this will be the PE to the RT power is what you want to use on that then. Okay? Just set it up, use your calculator. Okay, we got an answer? Doesn't take very long. What do you get? 267.91 is what I got. Okay, is that good? Okay. So, yeah, that would be a money amount. That would be $267.91. So anytime the problem says continuous compound interest, that's what the formulas you use. Okay? You just got to know that, all right? And then the E key, you got to know where that is and everything. Everybody okay with what we did there? Okay. All right, very good. Let's go ahead and let's break until like 11 o'clock. This one, we're going to kind of look at some of this stuff graphically. So this example 6, it says that you have $5,000 invested in a savings 4-year CD. It earns 5.61 continuously. So when it says continuously, you immediately will want to know that this problem has something to do with that formula. And then we're going to graph the amount as a function for a period of 4 times. We're going to look at this graphically because that's a really helpful thing to look at in a problem like this. So to begin with, let's get this set up, then I'll show you what we're going to do on the calculator. So in this problem, let's see, you start with $5,000, so your principal's $5,000. Let's see, the interest is 5.61%, so you'll have to move the decimal back on that. But what we're going to do on this is we're not going to do anything with t. That's going to be just be a variable. So what we'll see when we graph this is we'll kind of see how the account grows over time. Okay, so we'll set this up like this. We'll say A is equal to 5,000 e to the 0.0561. Always be careful about how you move decimals back. I see students do that all the time. And what you're really doing on a percent is this. Sometimes students have never made this connection, but the word percent literally means out of 100. That's what it means. So if you take 5.61 and divide it by 100, anytime you divide a number by 100, the decimal goes back 2. Okay, that's what you're doing. Percent is out of 100. Okay, so make sure that you do that correctly, and then put the t there. Okay, so that's what we're actually going to graph is this. Okay, so I'll kind of get you set up how we're going to do this on the calculator then. So in the calculator, what we want to do, I'll write down what you're going to do. You're just going to put in y1, you're going to put in 5,000 e to the 0.0561, and of course you'll have to use x. Okay, so let me show you how to do that. There's 2 ways you can do this, e by the way. I showed you the e above the division. There's also, if you look in your first column, the ln, that's called the natural logarithm. You'll see e to the x. I'm going to use that on this one this time. Just saves you like 2 seconds. So I'm going to go to y equals, then I put in what I've got highlighted in blue here, 5,000. This time I'm going to go to second ln, and see it just gives you the e and it already gives you the exponent. That's the only difference. Okay. Then I put in 0.0561 and then put your variable x like that. Okay, so that's how you're going to get that set up. And then we got to think about a window. So one of the things you got to learn as a student is how do I figure out the window on these problems? Okay. All right, so what I'm going to do on this is it says graph the function for a period of time over 4 years. So what that means to me, this is going to be your time, and that's going to be in years. So let's just go out to 4 years. Okay, so that's like a 1, 2, 3, 4. That's built into the problem. We're going to see what the account looks like in a 4-year time period. Okay, so here's what I think about on the y-axis. Okay, so the significance of that 5,000 is that's where your account starts, right? So you know that this first value is going to be 5,000. then what's it going to do? It's going to grow because of the interest. So what would be kind of a good idea to me is maybe to go from 0, and then you need to pick something bigger than 5,000. How big, I don't know. We can kind of experiment with that. So this is what I'm going to do on the window. So I'm going to go 0 to 4 by a scale of 1. That's my time in years. And then I'm going to go 0 to, let's say, 7,000. Okay, and that should be fine. And then maybe scale that by 1,000. Okay. All right, and then let's just set that up. I'll let you get that put in, and then I'll just kind of start putting this on here. Okay, so there's the 5,000. You can put K, that stands for 5,000. And then we're going to go all the way up to 7K like that. So this would just be dollars is what you would have there. Okay, all right, so I'm going to graph that now. If you got your window set up, then just go ahead and graph it and see if you get what I get. So it's kind of like an exponential function. It looks like a line. It's not a line. It's actually a curve, but it is growing. You would expect your account to grow over time. Okay, so what we're going to do is just get some points, and you can do this if you want to. An easy way to do this is just go second graph to open up your table of values, because all we're doing is going out to 4 anyway. Okay, so I'm going to start at 0. Let's just plot a few points. So first of all, notice you have the 0.05 That's what we would expect, because that's how much money, that's what your principal is, right? Okay, and let's just take a couple other ones here. You can just take one other one if you want to. So what I see on here is at 4, I'll try to zoom on this here. At 4, I see that you're about at 6,250. So I'm just going to kind of estimate that like that. And that's good enough, okay? All that's happening on this is going to look like a line, but it's really technically some sort of a curve, okay? It's not linear, so that's how that goes, right? So what that would do then is this would tell you, and see, using technology, this is what you do on spreadsheets and stuff like this. This would tell you that if you went all the way to 10 years, then your account would be all the way up to $8,762.10, right? So if you look at your table, that gives you those values very quickly, okay, like that. That's the idea. Okay, everybody with me on that, what we did? Okay. Graphically is kind of an important way to look at these problems sometimes. The next couple of problems we're going to do algebraically, but I'll also show you how to do graphically, okay? Okay, so let's look at this one. This requires a little algebra background. I think most of you either took college algebra or finite math. You would have talked about logarithms, at least a little bit. So you're going to have to use logarithms in this class a little bit. So what this problem is saying is it says how long. And when I see how long, that means in my formula I got to find t. Like I got to find the time. And it says an investment of 10,000 is going to grow to 15,000, and it's invested at 9% compounded continuously. Okay, so we're going to do this algebraically, then we're going to do it graphically. Okay, what formula do you use if it's continuous compounding? The PERT thing, okay? So it's A equals P e to the RT, okay? Your shampoo, you wash your hair with this formula, okay? All right, so what we do is, now what would P and A be in this problem? Which one's P and which one's A?
A is 15,000.
Yeah, A is what you end up with, right? P is what you start with. So I know that 15,000 is A because it's bigger. So what we're going to do is plug in here. The 15,000 will go in there. The 10,000 will go there. And then the only other thing we know is we know the interest rate, which is 9%. T is going to be the variable. So when you set this up, you would have 15,000 is equal to 10,000. Then we'd have e to the 0.09 times t. Okay, now generally in college algebra finite, you learn how to do these same kind of problems. And what you have to do is do logarithms. We'll be doing a kind of a logarithm review next week and everything. The first thing you got to do is you have to isolate that e part. That has to be by itself. The way to accomplish that is to divide both sides of your equation by 10,000. Okay, and then that will isolate the e part. So that would come down and you would have e to the 0.09t. You could take your calculator on this, and if you do that, all those zeros cross out. So you get 1.5, okay, if you do that. And now what happens, anytime you're solving an equation where the unknown is in an exponent, we call that an exponential equation. You got to use logarithms to do that. Okay? If you don't have a good background for logarithms, you'll get better at that because we're going to work on that a little bit next week. So what we're going to do is take the natural logarithm of both sides. And then there will be a few things I'll see if you remember about. The reason I'm doing a natural logarithm is because it's advantageous because of v. Okay? Now, do you guys know what to do next?
Divide.
There's a property of logarithms you learn. There's something you can do with this exponent. Yeah, you can bring it down. Okay, that's a property of logs. Okay? Some of this stuff you may not remember. So that's ln 1.5. Bring that down. That's a property of logarithms. So that's 0.09t times ln of v. Okay, and what that does, that gets the t in the exponent. Okay? If you don't know this, ln of v is equal to 1. Okay? I'll give you a very fast review on this. The reason is a natural logarithm is a logarithm of base e. And if you're doing that, it's equal to 1 because e to the first is equal to e. If you've forgotten all that stuff about logs, we'll get to that next week. On this kind of thing, I want to show you the methodology that you use on a logarithm here. So this would give you ln of 1.5. That just becomes 1. ln of e is 1. So you end up with 0.09 times t. Now what you have is a basic equation. If you want to isolate t, what do you do to both sides?
Divide.
You divide by 0.09, exactly. Then you're ready to get your calculator out, and that'll give the time that we're looking for. And then I'm going to show you how to do this graphically here in a minute too. All right. Okay, so what we'd have, just take your natural logarithm key, ln. I'll do that on a clear screen. Okay, so we go ln of 1.5. Be sure you close the parentheses. And then divide by 0.09. That 0.09 is not in the log, so you do that. And we'll round it off to like 1 decimal, so that will be about 4.5 years is about how long it takes for that to happen. So basically, if you're looking at an investment or something, and you want to kind of figure out how long it would take for that amount to grow in that, that's kind of what you could do. CDs are kind of good examples on that. If you invest, I have some CDs for retirement, so there's kind of, I might have a goal, so I kind of know where I'm going to be, like, in 10 years or something like that. Okay, so those are kind of helpful things to know how to do. Okay, any question about what I did? Does that logarithm thing at least look familiar? Okay. All right, because we'll see that a lot in here, and we'll work a lot on that next week. So what I'm going to show you next is how to do this problem graphically. So what we're going to do is we're going to do two things. In your calculator, you're going to put in, you're going to use the PERT formula. So we're going to start with $10,000, and then we're going to do e to the interest is 0.9%, but then we're just going to put like an x there. Okay, because we're trying to find x. What you're going to do in y2 is you're just going to put 15,000 because that's what we're expecting that investment to grow to over time. So get your calculator out and let's put these two things in. Then I'll show you how you can do this problem totally graphically then, which is kind of nice, kind of a nice thing to know how to do. Okay, so I'll put in y1 10,000. Okay, then I'll go e raised to the 0.09x, okay, like that, and then go to y2 and put in 15,000. And then we want to talk about a viewing window on this problem to get this put together, okay? Okay, so I'll slide that over there. If you need to look at that, that's what I put in. Okay, now the window goes like this. Our answer was 4.5. So what I'm going to show you is, let's go out something bigger than 4.5. Let's actually go all the way out to 10, go like that. Okay, that's going to be the time. What do you think would be a good Y window? 0 would be where you'd start because money, but how high would you have to go up to? At least 15,000, right? Okay, because you're eventually going to breach 15,000. Let's go bigger. Let's go 20,000. Okay, then maybe scale that by 5,000. Oh, not that, 5,000. Okay, I'll slide that over there if you need to get that put in. And then let's graph that and see. What you'll have is you'll have two graphs. The first graph is the interest, and then the second graph is the 15,000 like that. So that intersection point's what we're looking for then, okay? Now I'll show you kind of what I want you to draw on your paper. So I'm going to have you just sort of sketch out what came on the calculator, and this is essentially what I want you to do on this. Just kind of make a sketch. This will go out to 10. This will be your time in years, and it doesn't have to be perfect. It's just, you know, get some relatively close numbers there. This was going all the way up to 20,000, so I'll put 20K, 10K, that's your money like that. Okay, so what happens is this one is the 15,000, and then that's what you're looking for, is that right there. So you just need to get your axis set up and draw a picture of that. And then this thing started at 10,000, so it's important that you at least get that point as 0 and 10,000. Okay, like that. All right. So what I was going to do is I'm going to show you how you can do this on the calculator anyway. So I'll write down the keystrokes in case you need to do that. But if you got that viewing picture on your calculator right now, what you do, and I'll write down the keystrokes, and you can write them down if you need to. We're going to go second trace first of all. So that's the first thing we're going to do. And then when you do second trace, you should see a intersect command. So we can actually find the intersection. So we're going to go, the second thing is we're going to go down to option 5 where you do the intersection. Then the third thing is just press enter, and then I'll show you what to do. Okay, so I just do that, press enter. What will generally happen is a cursor key will be on one of your curves, and it needs to be close to the intersection point. You can use your left and right cursor keys to move around, but just get close to it. That's good enough. Then press enter. Then another cursor will come up on the other curve. If it's close to the intersection, press enter. When it says guess, press enter. And then it should, when it's done, blink on that intersection point. So what that intersection point is giving you is 4.5, comma, 15,000. Okay? So that's the same thing we got algebraically. That's the amount of time. And then, of course, that's the dollars. Okay? So you just go like that. Second trace, intersect, and then get those two, get your cursor close to the intersection point. Is that working okay for you guys that are doing that with me? Okay, very good. Okay, it's nice to know how to do that feature on the calculator. Ultimately, you want to be able to do these things both ways. Okay, I'm going to do one more, and then that'll close this section off. Any question about what I did on the graph? Yeah. Okay. Did I do something with your calculator the other day? Seems like I did. Okay. Yeah, it's a beautiful pink calculator. I think on this one you have to have that equal sign highlight. Okay. Yeah, and what I did on that, see if I get it blinking on the equal sign, it's only going to graph on your calculator, the one where it's highlighted. So I highlighted it, and I think that's it. Hold on. See it on the I'm going to try this. I'm going to go here. Show me how the class we got done. You might do a little Google research, because you need to know how to do that. I have seen that before, but I can't remember how to do that.
Yeah, so like mine, like I feel like the intersect and everything, but like when I do like, so like for example, when I do like the first curve, and then I go down to the other side, like you said, it like doesn't like it just keeps passing the second.
Okay, it could be I'm gonna do this again. I'm gonna get the cursor so I'm pretty clear that it's where it is. I'm gonna move it a little bit like that. Press enter. See, the second one's in good place. I think you may have had your,
So where did you do
I
this?
think you had your cursor too close to the cursor. Calculator didn't. Yeah, I just, see what I did is I went like this, option 5. Okay, see, if you have it right on there, then it seems like it doesn't work very well. I just moved it so, okay, I know I'm close enough. Press enter. Now I can clearly see the next one. Press enter. I think you were too close to the intersection. When the calculator didn't know what you were doing. Okay, that's kind of the idea. Okay, so let's go to the last page here and let's do this one. Okay, this one we'll just do totally algebraically. This one could be done graphically too. This one says how long, which means find t. And will it take money to double? And it's going to be invested at 4% compounded continuously. Okay, so you would want to start by writing down the correct formula. A equals P E to the RT power. Now notice I didn't give you any money on this. It doesn't matter, okay? Because what happens is if I started with $1, it would take the same amount of time for $1 to double as it would $1 million or $1 trillion or whatever, okay? It's just the way this works out. So what we're going to do is just choose whatever you want to, but the easy way is to choose P equals $1. That's the easiest way, okay? So what we're going to do is just put a 1 in there, and then the 0.04 is your interest rate, and then we're trying to find the time anyway. Well, if P is 1, what's A? 2, exactly. You can use whatever you want to, but keep it simple, 1 and 2. Just don't use 0 for P. Anything else will work, okay? So what you would get is you would get 2 equals, and then I'll just do 1 times e to the 0.04 t like that, okay? That 1 is not necessary. I just wrote that on there to emphasize that. Now it's all the same. You're going to do a log of both sides, like we did on the last problem. So do natural log of this side, natural log of this side. And then remember what you can do is the property of log says the exponent comes down. So you'd have ln of 2 equals 0.04t times ln of e. What did I say ln of e was? If you forget that, you can do it on your calculator. I mean, you can do that on your calculator. So that would just give 1. So what I would end up with then is I would end up with ln of 2 equals 0.04t. Then I can divide both sides by 0.04. I go to the calculator, and then that'll give the what we would call the double time on that then. Okay? All right? And let's see. So just go ln 2, divide by 0.04, and that'll give 17, I guess it'd be about 17.3, I don't remember if this was years or months in this problem. I think it was years in the problem is what it said, I think anyway. No, it didn't say, so we're going to assume it's years. You're pretty well always going to assume that that it's in years. Okay, so that's it. And it would turn out that if you had $10, it would take 17.3 years for the 10 to double to 20. It's the same always. Okay, that's the idea. So that's what I want you to know. Okay, any questions on that? Okay, this should be a good section.